give a talk. Before his talk, let me briefly introduce Professor Andrew Wei. Professor Wei now is a professor of physics and the director of surface science laboratory at the National University of Singapore in US. He was a Commonwealth Fellow as well as Rhodes Scholar at the University of Oxford, where he received his Doctor of Philosophy in 1990. He holds a Bachelor of Arts honors in physics in 1984, as well as a master's degree from the University of Cambridge. Now he is an associate editor of the journal ACS Nano and serves or has served on several other journal editor boards. His research interests are in surface and nanoscale science, scanning tunneling microscope, Stm, and the synchrotron radiation studies of the molecular substrate interface, graphene, and related 2D materials. Today, he's going to talk about ferromagnetic 2D materials. Let's welcome Professor Andrew Wei. Andrew, please.
Thank you, Hua, for the kind introduction. I'll share my screen now. Oh, unable. Oh, someone needs to unshare first. Right. Okay, can you see my screen?
Yes, please.
Okay, thank you. Thank you, Hua, for introduction. My pleasure to give this Smart Math online lecture. Thank you very much to organizers. So let me first show you the members of my group, since they are all the people that really did all the work. And my group is working on many areas, not just 2D ferromagnetic materials. In fact, we started working on 2D ferromagnetic materials only about 3 years ago. And our first paper was only published in 2019. So I'm going to present fairly recent work from our group. Our group also works on the molecule substrate interface and some 2D related devices. So for today, I'm just going to highlight the work of just these 6 people in my group. I'll briefly introduce them, but I will introduce them a bit more when I refer to their papers. So at the bottom left, you can see Johnny Wong and Zhang Wen. Both are now professors at Northwest Polytechnical University in China. So they were postdocs in my group. And from the right to left, with faces circled, I have Dr. Huang Yuli, who's a postdoc, and then PhD students Rebecca Chua, Chu Rui, and former PhD student Zhang Lei, who's now a postdoc. So my surface science lab in the US, like surface science labs everywhere, it's mainly made of ultra-high vacuum systems, like STMs, AFMs, MBE, RPAS, and we have an OSK lab. In today's presentation, I'm going to talk about ferromagnetic 2D materials. So we collaborate with other colleagues to do magnetic measurements because obviously we don't have all the equipment. But nevertheless, I'm also affiliated with 2 centers in NUS. The first is the Singapore Synchrotron light source. You see a picture on the bottom left. It's on our campus. We have a small superconducting synchrotron ring, 2nd generation, and we built a beamline about 20 years ago. Oh, no, sorry, it's 30 years ago. The SINS beamline, surface interface nanostructure beamline, as seen over here. This is where we can do RPAS and where I will show some Xmcd results. And the next center that we are affiliated to is it's a newer center, the Center for Advanced 2D Materials. And its most important facility is a clean room. We have a class 1000 clean room there, which is very useful for our students who need to make device first from 2D materials or stack 2D materials and do routine characterization methods. So let me talk about the scope of my lecture today. So I'm assuming the audience is fairly general. I know some students in my class and my graduate students might be on as well. So in view of that, I will give an extended introduction to 2D magnetic materials. And then I will ask 4 questions basically in this seminar. The first is there intrinsic ferromagnetism in 2D materials? And to answer that, I'll talk about 2 of our papers on 2D vanadium diselenide and 2D vanadium ditelluride. And the second question is, if there isn't magnetism, can we magnetize these 2D materials by proximity doping or doping? And I will show our work on cobalt-doped 2D VSE2. And the third question is, what are the effects of defects on magnetism? And the final question is, how about magnetism in the heterostructures? And I'll talk about Churei's work in the nanolattice. And I'll end with some future perspectives of this field. So the motivation of our work, as in much of the research in 2D materials, is perhaps in the field of flexible electronics. As the materials are just one monolayer thick, they are mostly flexible. So you can imagine making devices, and in this case, because it's magnetic, storage devices on clothing or on your wrist and so on. So 2D magnets, if they are possible, can be used for non-volatile storage, spin filtering, spin injection, and detection. And they could be combined with the well-known 2D material graphene, which is known to have long spin diffusion lengths and weak spin orbit coupling. And the 2D materials that I'm going to talk about, and many people are working on, are the transition metal dichalcogenides, because many of them are not just metallic, but they could be semiconducting, they could be superconducting, and of course the question mark, could they be magnetic? And they have a strong spin-orbit coupling because they're heavy metals inside, and they obey Valley optical selection rules and so on. So there's a lot of potential for 2D materials for spintronic heterostructures. I'll give you a brief introduction on 2D materials. It's basically from Wikipedia. So after the discovery of graphene in 2004 that everyone knows, people have been studying the whole family of many 2D materials. But it was not until 2017, just 3 years ago, that the first 2D ferromagnets, CRI3, chromium triiodide, and CGT, this chromium germanium telluride, were fabricated. So this is a very new field. It's just 3 years old if you count from this landmark paper. And one of the reasons is that in 2D materials, thermal fluctuations tend to destroy the magnetic order compared to the 3D equivalents. And low-dimensional materials have different magnetic properties compared to the bulk. So you can measure this transition from 3D to 2D magnetism. And it has been observed in the iron equivalent FGT. And they have many potential applications, as mentioned previously, in van der Waals heterostructures. Okay, so this was the first paper that was published in Nature. It was done by the group of Xiang Chang, who's now the president of Hong Kong EU. So those of you in Hong Kong, he's someone very close by. He was at Berkeley then, and he led the team at the Berkeley lab who discovered this magnetism unexpectedly in this 2D material. And this 2D material was chromium triiodide, and you see the MOC spectra on the right, where you can see the typical hysteresis loops that you would expect from a ferromagnetic material. So obviously, this created quite a splash because there could be lots of implications for spintronic devices and so on. And this study was important because it tackled a long-standing issue in quantum physics about whether magnetism would survive when you shrink a material from 3D to 2D. Because for half a century, the Mermaid-Wagner theorem addressed this question by stating that 2D materials lack what is known as magnetic anisotropy, and because of a directional alignment of electron spins in material, there may be no magnetic order. So this study really addressed this theorem. And the key to this study was they found that you have to create some magnetic anisotropy in a 2D material before you can get intrinsic magnetism. So we wrote a review last year, a brief review in InfoMath, and it basically summarized the field in this way. In the field of 2D spintronics, one of the key things is having 2D van der Waals magnets. And of course, we have both magnets that are intrinsic, like the ones mentioned, and extrinsic, where you induce magnetism by defects or functionalization or doping and so on. And the key to using these 2D materials in applications is the ability to grow good quality, large area or wafer size 2D materials. So advances in growth and characterization techniques are being researched on, and MBE tends to be the technique of choice because you can control the growth very well down to the monolayer limit. And this is the technique that I will talk about in our group. And of course, you need nanoscale magnetic characterization tools. And challenges and opportunities on the left, obviously, are scalability, the stability of these materials in ambient. You want high or above room temperature Curie temperatures so that the magnet remains magnetic at room temperature, where most devices operate. And of course, there's a whole range of interface-induced magnetic phenomena that are very interesting to physicists and material scientists. Another review that came out just last year was by the group of Kostya Novoslov, who's now in NUS. So essentially, they summarized the field at that point in time and emphasized that in 3D system, a magnetic phase transition can always occur at a finite temperature. So you always see a Curie temperature transition in the 3D system. On the other hand, in a 1D case, you can only get long-range order at 0 Kelvin. In other words, you can't get long-range order at room temperature. And the 2D is complex. It's in between 3D and 1D. And the existence of magnetic long-range order at any finite temperature depends crucially on the number of spin components, usually called the spin dimensionality, and determined by the physical parameters of the system. So what does this mean, spin dimensionality? So this, in the next slide, in their figure 1 in the paper, they explained it. So you see 3 classes of 2D materials with spin dimensionality 1, 2, and 3. So let's go. The Mermaid-Wagner Hohenberg theorem states that thermal fluctuations destroy long-range magnetic order in 2D systems at any finite temperature when the spin dimensionality is 3. And this 3 is the isotropic Heisenberg model. So the spins are able to point any direction. And in this case, thermal fluctuations will destroy magnetic order. So you don't see any Curie temperature. There's no transition to magnetic order in the 3D spin dimensionality 3. On the other hand, on 1, spin dimensionality 1, this is the 2D Ising model where the spins can only point up and down, right? You can see a phase transition to a magnetically ordered phase at a Curie temperature, a finite Curie temperature Tc, as shown here, right? That's because a gap is open in a spin wave spectrum and it suppresses the effect of thermal fluctuations. So in the n equals 2 case, which is the case of the planar 2D magnets as shown, the model here is known as XY model. It shows no conventional transition to long-range order, but Berinsky, Kotelitz, and Taulas, these are Nobel laureates for topological insulators, pointed out that you can get this kind of divergence at a particular temperature with the onset of topological order. And it's characterized by the decay of spin correlations and the presence of bound pairs of vortex and anti-vortex arrangements. So this Kosterlitz-Taulas temperature, TKT, below it, which quasi-long-range order, magnetic order is established. So you can sort of achieve magnetism in such a system. So the only equation I'll show here, basically what I've mentioned about spin dimensionality can be summarized by this generalized Heisenberg spin Hamiltonian. So you see in this equation, three terms. You see the first term is this J as well as I as J, which is where J is the exchange coupling between spins Si and Sj on neighboring sites, okay? And if J is greater than 0, it's ferromagnetic. If J is less than 0, it's anti-ferromagnetic. So this is the basic basis of magnetism. But you have two other terms, A and gamma, where they are known as the on-site and inter-site or exchange magnetic and anisotropies respectively. So A is the on-site and this is the exchange, right? And it turns out that for isotropic Heisenberg model, that's n equals 3, where you have an absence of magnetic anisotropy, A and gamma is about 0. Hence, that's why you can't get magnetism. But in the Ising or the XY model, n equals 1 or n equals 2, in the limit of strong easy axis or easy plane anisotropy, where A tends to plus or minus infinity, so it's non-zero. This model can take into account all the effects that shows some kind of long-range order. Okay, so this is a Hamiltonian that governs 2D magnetism. Okay, and then Xiang Zhang also wrote a review in Science that summarizes all the possible van der Waals magnets that we have. So this is the van der Waals magnets library. This is, of course, in 3D. And in green, you have those possible bulk ferromagnetic van der Waals crystals. In orange, you have the anti-ferromagnets and so on and so forth. But let's focus on the green ones, the ferromagnetic. And as mentioned, the Mermaid-Wagner theorem states that at any non-zero temperature, the long-range order cannot truly exist. But you can create a magnet excitation gap capable of resisting thermal agitations if you introduce some anisotropy in this unit, in the material. And you can introduce a magnetic anisotropy, and in fact, magnetism has been displayed in the materials which I've circled above. As you can see, the chromium iodide is here, CGT, FGT is here. And now, the vanadium diselenide, I put it in red dots because there's a bit of controversy, and I'll be talking about this. So, the first question, is there intrinsic ferromagnetism? Of course, the answer is yes, because they discovered chromium triiodide, CGT, FGT. But how about these vanadium materials? As I mentioned, theory predicted there should be magnetism in these class of materials and also some other 2D TMDs. So if you look at the periodic table, the 3D transition metal series where there are a lot of unpaired electrons, you would expect some of these, their dichorgonites to be magnetic in the 2D limit. And these two materials have been studied recently. The manganese diselenide and the vanadium diselenide. So this is the study on the manganese. Oh, sorry. This is another review paper that summarizes and plots the Curie temperature of all these 2D materials. That's room temperature, 300 K. And as you can see, why we're interested in manganese diselenide and vanadium diselenide is that their transition temperature or Curie temperature is above room temperature. Hence, they can have the potential to be used for devices, right, at above room temperature if they are magnetic. So let's talk about manganese first. So this paper was reported by Kawakami's group in UC Riverside 2 years ago in Nano Lattice, and they showed that 2D manganese diselenide is a ferromagnetic. So you can see slight hysteresis here, and so that, in a sense, helped stir up interest in the field. And in the same year, the Batzels group in Florida reported strong room temperature ferromagnetism in vanadium diselenide. So you see this hysteresis loop, and essentially, theories have already predicted that the vanadium ions have a value of 0.6 Bohr magneton per vanadium ion, although it's smaller than other 3D ferromagnets like in iron or cobalt. And they reported, strangely, a huge value that is about an order of magnitude larger than the theory. So this was something that was not explained in the paper. And this inconsistency cast doubt in the use of bulk magnetic tools, because they use bulk magnetic tools to measure these MH curves. And this is the challenge whenever you're trying to measure magnetism on very thin 2D layers, where you're trying to get weak signals from a large background. So we are not saying this results are wrong, but we are saying that similar to the field of dilute magnetic semiconductors, where you can get unintended magnetic contributions from various sources. So it could be that there are contaminations, or it could be that there are defects on the samples that lead to these observations. And that's why in this case, the value of the magnetic moment is so much larger than that predicted. So KIV, this Nature Nanotech paper. Now, we published the following year in Advanced Materials this paper on evidence of spin frustration. In fact, this paper was mainly done by Johnny Wong, and you see his picture there. He's the one in Northwest Polytechnical University in China now. He's a professor there. So, in fact, he started work on this about 3 years before, but took a long time to publish because he did not find the expected magnetism. But we decided that the new result is also an important result. And in this case, especially since the Nature Nanotech paper came out, he showed that if we use Xmcd, so you see in C here, this figure, because we have a synchrotron, if you look at the dichroism signal, you can get information on the spin and orbit moments. And by taking the different spectra of two helicities, in a synchrotron is polarized light, so you can take the clockwise and anti-clockwise spectrum above and below the plane of polarization. And the different spectrum shows that within a 0.1 or 2%, there's no XMCD signal. In other words, this is MBE grown, so we've grown it very carefully, and we believe it's fairly good quality. We don't see magnetism. And these here are the Stm images. They are interesting charge density wave patterns which have been reported separately, and we are also working on another paper on some of this. And you see in this phase, it's semi-metallic, and you can open up a small band gap. I mean, there is a small band gap here in this. This is 1T phase, I believe. And yeah, so although theory predicts that it should be magnetic, we did not observe magnetism. And in fact, we did other magnetic measurements. Squid also shows no sign of magnetism down to 2 Kelvin. And the linear is anisotropic, and you get higher moment in the out of plane direction than within the 2D plane. So we inferred it is paramagnetic in the outer plane, and negative slope means it's diamagnetic in a 2D plane. And it could be due, the latter could be due to the substrate background. And you see overlap in the zero field and field cooling curves indicates an absence of long-range magnetic order. And a broad maximum in the susceptibility indicates some short-range anti-ferromagnetic interaction. So this paper essentially says that in this system, there's evidence of spin frustration. So you can see in this hexagonal diagram here, if this is spin up and spin down, you have a frustrated spin here, which could either be up or down. And these two are anti-ferromagnetically coupled. So that paper questioned the other paper, Nature Nanotech, that this material is intrinsically ferromagnetic. So we went on further, Johnny went on further to work on the sister TMD, vanadium ditelluride, right? That's very similar. And not surprising, in this case, there's some STM and RPS data, but I just wanted to show you the Xmcd data. Again, the Xmcd signal, basically it's zero. The different spectrum between the two helicities is zero. So we also deduced that this VT2 is non-magnetic, which then further supports our initial observation. And it turns out that later on, the same group, Batzel group, reported in JPCL on vanadium ditelluride. And this time, in their paper, of course, they were talking about the charge density wave, but they did XMCD this time, and you can see the XMCD signal here. And they agreed that vanadium ditelluride is non-magnetic. So this time, the same group that reported magnetism in VSE2 did not see magnetism in VTE2. So I think this suggests that there's a different explanation for the first report, and I'll be coming to that. But before I come to that, I'll just then ask the next question. If we had a spin-frustrated system like VSE2 that is non-magnetic, but on the verge of magnetism, can we make it magnetic by proximity first, right? And that brings us to our work on cobalt on 2D vanadium diselenide. And this work is done by Zhang Wen, who also has a professorship in NPU. To summarize, the title says magnetic transition in monolayer VSE2 via interface hybridization. So essentially, as this table of contents diagram shows, you put cobalt on top of VSE2, it makes VSE2, it induces by proximity magnetism, and it is anti-ferromagnetically coupled, because you see from the XMCD signal, these hysteresis curves are in opposite directions. And just to elaborate on that, so here's STM showing the islands of cobalt or clusters of cobalt on top of vanadium Se2. And then you see the cobalt XMCD signal and the vanadium SMCD signal growing as the coverage increases. But the peaks are in opposite directions, and that leads to this hysteresis in opposite directions, cobalt here and the vanadium in the other direction. And essentially, that is evidence for anti-ferromagnetic coupling between cobalt and vanadium Se2. So we demonstrate here that even if here in this case about 3 monolayers of cobalt can cause vanadium to become magnetic, and vanadium diselenide, which was initially intrinsically non-magnetic, right? So this is basically the direct evidence for that. So we are continuing this work, and I'll say a bit more about this at the end of my lecture. But other people, other people have also observed that you can make non-magnetic TMDs magnetic by doping, which is another method, of course. Of course, doping of a 2D material is a little bit more challenging. You're basically substituting atoms within the one layer. And in this case, the Betzel group, again in Florida, managed to make molybdenum ditelluride magnetic by incorporating vanadium impurities. So his work, this work suggests that such impurities could make a non-magnetic TMD magnetic, which also then raises questions about whether it was impurities that caused the initial vanadium diselenide work in Nature Nanotechnology to induce the magnetism there. And several other people in different systems. So this is a NatureCom article that appeared, I think it was last year, showing that you can induce both luminescence as well as ferromagnetism in MOS2. And that's a diagram showing the mechanisms involved. Because of suppression on non-radiative recombination, you can get PL, and because of spin polarization, you can get ferromagnetism. And the data is here, but I'll concentrate on the ferromagnetic. So you can see these hysteresis loops over here, and you can see in the figure the labels. Cobalt and chromium dopants were both used here. So again, an evidence using a magnetic impurity or dopant, you can induce magnetism in a non-magnetic 2D material, in this case MOS2. And another paper, this time iron is used, a magnetic dopant iron MOS2. You can see the hysteresis loops here. So that answers the question, yes. Although many 2D TMDs are non-magnetic, there could be some spin frustration, which could make it magnetic by doping, okay, or proximity doping. So I come to my third question now, and this question tries to answer a possible reason for observation of magnetism in those intrinsically non-magnetic 2D materials. What is the effect of magnetism? So this paper, which was published last year by, I'm sorry. Okay, this paper is done by my colleague, Kemping Low, in chemistry department. And this time, being a chemist, they produced the VSE2 by chemical exfoliation, unlike our method by MBE. But of course, a chemical exfoliation method does raise the concern about whether you could introduce impurities in your subsequent measurements. So their magnetic measurements shows evidence of magnetism. You can see a little bit of hysteresis loop in what they call pristine vanadium Se2. But what was more revealing is that when they heated this VSE2, the magnetism became stronger, and they explained this by measuring the vanadium to selenium ratio. So the ideal intrinsic pure vanadium Se2, the ratio Se to vanadium is 2. But as they showed here, as they annealed it, in fact, they showed that what they actually grew was vanadium selenium 1.75. So there are possibly some vacancies or some loss of selenium in the growth process, which is not surprising since selenium is the more volatile element here. But upon annealing, okay, they did two things. First, annealing. Upon annealing, if you look at the vanadium Se 1.5 1.75 plus O2, what happens is the magnetism drops, right? If they annihilate in air, oxygen. Or if they put a thiol on top to, in a sense, quench those vacancy defects, then the magnetism also drops. So the conclusion we came to, of course, is that perhaps it's the vacancies that enhance the ferromagnetism, and these vacancies can be quenched by thiols or oxygen. So that would be our explanation for this. Okay, so that brings us to the paper by Rebecca. That's she's writing up a thesis now. So her paper directly questions whether selenium deficient defects can induce magnetism. In this case, the defects we were working on were line defects. So if you look at the figure on the left, you will see that initially the vanadium diselenide has a low density of line defects. And if you anneal it to 400 degrees centigrade, you can see these line defects starting to appear. And when she annealed it to 430 and then 470, there's an increase in density of line defects. So diagrammatically shown in the schematic below. So you can increase these line defects just by annealing. They form triangles because it's just reflecting the symmetry, the hexagonal symmetry of the vanadium diselenide. And these high resolution AFM, we also have AFM that allows us to see the topography of these line defects, and looking at these atomic resolution images of these line defects, we can draw the structure of the vanadium diselenide, in particular the surface selenium structure, and we can construct this line defect which is essentially a selenium deficient line defect, and the reconstruction is formed by removing of this defect and a displacement by half unit cell. It gives this line defect. So we know we can form these line defects on the surface just by simply annealing the MBE grown VSE2. And we do the annealing in vacuum so that there's no oxygen around. So these are the magnetic measurements. First, the Xmcd measurements above. You can see that for the pristine vanadium diselenide, before you see that the Xmcd signal, the noisy line, is approximately 0. But when she annealed the sample in vacuum, and when there are more defects on the surface, you can see the slight dichroic signal appearing here, indicating that there seems to be a direct correlation between these line defects and magnetism in the surface. And these are below are MFM images of the surface, and you can see that E and F are pristine, and G and H are annealed, so it's defective. And if you look at them carefully, you can probably see that there's an increase in in magnetism in the defective structures. Okay, those bright high contrasts are due to the MFM phase regions being shown. And if you plot out from the spatial data the percentage of this surface in a different phase, because this is a phase image, you see that there's an increase in the percentage of this surface being at a different phase. And that's indicative of surface magnetism of the defective surface. So we believe that this has provided direct evidence of the effect of defects on what is probably an intrinsic non-ferromagnetic material, vanadium Se2. And we did some computations as well, a collaborator, and observed that if you move towards the more defective surface, you can actually increase the magnetization per unit atom. So the DFT supports this, and hence we propose this explanation in this paper. The reason for silicon deficient defects lifting the original frustrated magnetism previously reported for monolayer vanadium Se2. Okay, so I will summarize our understanding of vanadium X2 magnetism, where X is selenium or tellurium. Our focuses on MBE grown material, which guarantees the highest level of cleanliness and crystallinity at the atomic scale. The ferromagnetism, some papers like the Bonella paper reported magnetism at room temperature, but others did not, like us, did not reproduce these results. I mentioned KP Low's experiment where they did chemically exfoliated VSE2 and they saw some magnetism, but it could be selenium vacancy related. So the point about the absence of magnetism in monolayer VSE2 and VT2, we saw from our works and that of several others as well, that basically you don't see any ferromagnetism down to 10 K and 9 Tesla. But although they lack ferromagnetism, we can easily induce magnetism by proximity effects, for example, in the cobalt VSE2 system, or by various other magnetic dopants as mentioned previously. So this provides evidence that the material VSE2 and other similar ones are on the verge of magnetic transition. And the role of defects, our final study was to show that your silicon deficient defects could induce a uniaxial magnetic anisotropy that could open up a large Magnon gap, lifting the restrictions imposed by the Mermaid-Wagner theorem. So this is our current understanding of this system. So I'm coming to the end of the talk. My time is up. I just want to briefly mention magnetism in heterostructures because this is work done by Chu Rui and supervised by Zhang Wen, who's now in NPU. And essentially over here, we are moving our study towards devices. So we're studying chromium trichloride FGT heterostructures. And it's interesting because as this table of contents image shows that if we have this system of CrCl3 on FGT, the hysteresis loop shifts relative to the vertical axis, as opposed to the FGT where it's symmetric, right? So this shift is known as the exchange bias. This exchange bias is a physical phenomena whereby the spins of a ferromagnet are pinned by those of an anti-ferromagnet. And this is essentially the effect that underpins our magnetic data storage that we use today. Hence, this is very important. And just to show it a bit more clearly, this device configuration was made. This exchange bias was measured in their heterostructures. And if you want to know more about the paper, it's published this year in Nano Letters, and you can read about it there. And this is another review in nanoscale this year, talking about the possible device configurations that can be used if you have magnetic 2D layers. So it shows in A, it shows the 2D spin filter magnetic junction. Next is the bilayered tetralayer CRI 3-tunnel barrier. And in C, you have spin orbit torque configuration. And D, you have spin FET in D. And E, you have a spin valve structure. So you can see there are many different possibilities and configurations of spintronic devices that we can explore in the years ahead. So this looks like a promising field and hence I'll look at finally future perspectives of this field. And just to give you a taste of what we've been doing, because we are working on molecules as well in some of our other projects, I'll introduce the field of molecular spintronics. Hence, can we use magnetic molecules instead of these inorganic materials? And in fact, this article in phys.org in 2019 highlights the potential for this molecular spintronics in quantum computing. So they emphasize, well, it's hard to scale up, but with molecules, in principle, you can scale up easily because molecules are very small and they can be synthesized in chemistry lab. So by controlling and manipulating the electron spin in the molecule, we in principle can do quantum computations. And that's why this field is so exciting, right? So you can imagine a world where you can find out, so this is quantum sensors, what is happening under your feet, whether warning of volcano eruptions and so on. So these are some potentials of these quantum sensors, very sensitive sensors. In fact, magnetism in molecules has been previously discovered, and this is work done by an Imperial group published in Nature all the way back in 2013. Essentially, they studied copper tylosinane, this molecule over here. So it has a copper center and tylosinane attached to it. And they use, I think it's ESR measurements, and they measured basically the spin property and the coherence, decoherence, and relaxation times, and found that it is at near room temperature that the coherence times are fairly decent. So that's not far from those in the NV centers. This is diamond NV centers currently being the forefront materials. So there's potential to use molecules. So Zhang Lei in his PhD project was working on a related molecule, cobalt tylosinane, and he was working on cobalt tylosinane on vanadium diselenide, where we talked about earlier. So naturally, and of course in STM you can see the arrangements, and they self-assemble in this very nice periodic structure. So he did COPC on HOPG, see this square lattice, and COPC on vanadium diselenide, where it's slightly distorted lattice over here. So the question we are asking now, okay, can COPC, just like cobalt, induce proximity magnetism in vanadium Se2? Now, this work doesn't talk about magnetism, only talks about electronic effects. So that's our next work that he will do to see whether we can use magnetic molecules to induce magnetism in 2D materials, and hence it opens up new applications in flexible electronics using organic materials, which is being done now in organic OLEDs and so on. They are flexible devices using organics. Okay, I will end here since my time is up, and acknowledge all the people in my group, especially those marked in red whose papers I showed earlier, as well as my collaborators in IMRI, in Southeast University, in ALS, Diamond, where we did some synchrotron measurements, in NTU for some magnetic measurements, and 20 as well. And of course, financial support on all the funding agencies. Thank you. So I've ended the talk, and I'll be happy to answer any questions.
Okay, thank you very much, Professor Wei, for the wonderful talk. Here, I received some questions. One question is how to control the line defects in the VSE2 material.
Right. Okay. As you can see, the line defects are, because it is formed by thermal means, forming in this way, it is not very controllable because we were just trying to vary the density of the line defects. I'm sure if you try some other means, you may be able to control it. But in our case, all we were able to do is control its density as a function of annealing temperature. So that's my answer.
Okay. Another question is, what about the VX2 magnetism with amorphous structure? Structure.
That's a good question. My short answer is that we have not worked on any amorphous structure, so I do not know the answer to that. And it's because most people in the 2D field, if you want to make a 2D material, it has to be crystalline, otherwise you wouldn't make a stable structure. So 2D amorphous structures are really difficult to come by, and we haven't done the experiment yet, but perhaps you can try to do it.
Okay. So thank you. Then now I receive a new question. What's the role of cobalt ferrocyanide deposited on VSE2?
What's the role
of cobalt ferrocyanide, this COPC?
Okay, the paper I showed there, Zhang Lei showed, was basically we were studying the electronic structure, so the effect of cobalt tyrosinane on the vanadium diselenide electronic structure, and which follows from some of the many of our previous works where we studied the electronic structure at the interface between some molecule and some 2D material. But as I mentioned, what we are interested in now is whether cobalt tyrosinane, which is possibly magnetic, how it can induce a magnetism in vanadium diselenide by proximity, as we demonstrated by cobalt on the surface. Just using metallic cobalt, we can actually get VSE2 magnetic. So the complete answer to your question is not known yet. We are about to do the experiments, so we'll report it in time.
Okay, thank you. Another question is, what about the yield of monolayer VX2? The yield.
Yield of what?
The
monolayer VX2.
VX2.
Okay, in MBE, the yield is 100%. Because if you are familiar with MBE, you have evaporation sources in the vacuum chamber. And this is not chemistry, this is MBE, which is molecular beam epitaxy. You're evaporating atoms onto the surface. So the yield is 100%.
Okay, that's nice. Okay, the question is, what about the current challenge of electrically magnetic materials? The current challenge of electrically magnetic materials.
Okay, I think what you mean is what are the current challenges of magnetic 2D materials. Okay, as mentioned in the earlier slide, first of all, we have to find out which 2D materials are magnetic, because I explained earlier in this Wagner theorem that in theory, 2D materials cannot be magnetic, right? We saw the spin dimensionality in the 3D of 3 is not possible. But if you introduce anisotropy, if you limit the spins, you can induce some magnetism. And hence, recently I mentioned chromium triiodide, CGT, FGT, and of course this controversial vanadium diselenide. People are starting to discover intrinsic 2D materials. So the challenge is to find more intrinsic 2D materials, or if you can't find, then inducing these magnetisms by doping or by proximity effect. That means by putting an adjacent layer on it. So the challenge is to be able to then grow these films in large areas so that industry can make them into devices.
Okay. So, other questions? Return? What about, what do you mean about this?
I think
Also, the professors in this meeting room also can
right,
ask
same
some
thing.
questions.
Yeah,
Yeah.
I think just raise up some question about the recruitment, PhD recruitment, postdoc recruitment from students.
Okay.
Oh, if any of you are interested to do a PhD or postdoc in my group, of course, you're most welcome to send me an email. And of course, we have to work out what the funding is, but it's definitely possible. I'm always looking for people.
Yeah, that's a good news. For our students.
Yes. Yeah, if you want to find out more about Singapore, you can ask the chairman Zhang Hua or the Zhi Sheng. They have been live in Singapore, so they can tell you about Singapore. Yeah. Yeah, it's quite safe.
Yeah.
Sure. Yeah. And also Professor Andrew is a very, very nice guy, and research is a highly impact.
Thank you, Hua.
Yeah. So if no more question, I think we can stop here. Let's thank Professor Andrew again. Thank you, Andrew.
Okay.
Yeah. You
Yep.
have a nice weekend.
Thank you, Hua. Yeah, thank you. Bye-bye.
Yeah. Thank you, everyone.
Bye-bye.
Yeah.
Thank you.
Bye-bye.